right?
Yeah.
To get the flux,
integrate flux.
get the flux.
Yeah.
For you, how to calculate the error after the
Now I'm developing this part of the script. Yeah, so still to do this.
Okay, yeah, I'm thinking about how to estimate the errors, because the data every time the data have an error.
Yeah.
So what I get the integration.
Well, the also sort of t-square due to the fitting procedure. So
Yeah.
we try to minimize the error. So according to the procedure, you have sort of an error on results. Then you have to write this error maybe flux and integrate flux so you'll be able to, let's say, propagate the error.
Yeah, probably. Yeah. How to calculate the error from this step to this step to this step.
I can calculate this point. So I'm just without screen.
A little screen. Did you finish it?
I'm trying.
Trying to finish it. So probably after post this after post,
Okay.
Yeah, I follow you and discuss. Yeah, sure.
Okay, cool. Well,
Okay.
Esatto, 2, 3, grazie. Però poi possiamo mettere vabbè dai, io che 3
vuole cominciare?
Good evening. Let's start this journal club. Today we have two speakers. So our first speaker is Achille Fiore with a further test of Lorentz violation from the rest frame spectral legs of gamma ray burst.
Thanks, Mariano. Good afternoon. As you can read from the title of this talk, I am going to present you this paper about, as you can read, the Lorentz violation of left frame spectral leg of gamma ray burst. These are the three main concepts of this journal leg. Spectral leg, by definition, are time difference in the arrival of photons with different energy. I suppose that it may sound a little bit strange to us because photons are supposed to travel at the same velocity c. But anyway, this is a rather typical feature of gamma ray burst, although there is no agreement about the theoretical explanation of those spectral legs. And one of the possible hypotheses is that these spectral legs may be induced by a violation of the Lorentz symmetry, one of the milestones of our physics, as supposed by some quantum gravity theories. Here I resume you briefly the standard paradigm of special relativity. This is the energy momentum conservation, as you can see, but at this point, if we try to violate this relation, we can suppose that the left-hand right-hand side is not really 0, but equals to a function that is supposed to be negligible for energy lower than some energy scale that here I have called EQG as quantum gravity energy scale, up to which that function f should be anyhow sensible in a sense. So the requirements that we ask for the function f allow us to express it by means of a Taylor expansion. This is stopped at the first order. This is the square of the energy, and by solving the Hamilton equation, we have the so-called dispersion relation for photons. Okay, it may sound a little bit strange, but anyway, if we apply the time redshift relation of cosmology, we can retrieve the expected, by theory, spectral lag induced by violation of the Lorentz symmetry. So the strategy is the following. Delta T OBS, it is the observed time lag, because there are also data. Delta T LIV is what we computed so far, and B, the addendum B, is the contribution of an intrinsic time lag, because GRB has some geometry that we do not know, and so some delay might be due also to a geometrical factor. But this strategy, developed by Ellis and collaborators, allowed to avoid, in a sense, the contribution of an intrinsic spectral lag. But this strategy has a little problem due to the fact that the observed spectral lag is generally observed in the observer frame of reference, but as suggested by Uguotta and collaborators in 2010, if I will remember, it is more convenient to detect the spectral lag in the rest frame of GRB by choosing two fixed energy bands, and these, for some reason linked to the K correction in a sense, allow us to have a tighter correlation between the observed frame of reference and the rest frame reference. So I resume you which is the strategy of the paper. This is the observed time lag in the rest frame. This quantifies, in a sense, the violation of a Lorentz invariance effect. And so, knowing these two quantities, this is the intrinsic contribution. So, knowing these two quantities here, we can have an estimation of these two quantities here. The term here, A LIV, is what we have before with the integral. So, in order to resume you of this computation, A LIV is proportional to the energy difference. So, in a sense, to the velocity difference of two photons with different energy. So, we do expect that in the case in which we have Lorentz invariance violation, A should be greater or lower than 0. Different from 0 in a sense, non-zero. Data, finally, were taken by another work by Bernardini and collaborators about a sample of 56 GRBs that are redshift distributed between 0.3 roughly and 5.47, if I will remember. And the rest frame energy bands were chosen, as you can read, between 100 and 150 kilo electron volts and 250 kilo electron volts. These two bands were selected in order to fall anyway in the spectral sensitivity of the Swift instrument that the authors were using. These are the results. ALIV is tiny in a sense, and B is the intrinsic contribution. These fits were obtained by means of the maximum likelihood estimation and the chi-square method. This is the energy scale up to which we can neglect the contribution of the supposed quantum gravity effect. And so others claim that Lorentz invariance is consistent with the data. So we do not expect any violation of the Lorentz symmetry. I confess you that I was a little bit skeptic about this result, because yes, I can notice that ALIU is tiny, but compared to what? Yes, it maybe. So I tried to make a little computation of myself with little code in Fortran 19, and I tried to convert the energy difference contained in that factor ALIU in a velocity difference, and I recovered, as you can see, that this velocity dispersion is about 10 to the minus 9, that is roughly the order of the precision up to which we know the value of the speed of light in the vacuum. So, in my opinion, this result is reassuring, say, for the Lorentz invariance. Finally, the authors made also a test about possible redshift dependence of the Lorentz invariance violation. So they applied the method I explained so far to the whole sample, but divided in 4 bins of redshift, and they claim again that there is no appearance of redshift dependence, even though we can see the error bars of the second bins that is very large and optimistic. Anyway, I can stop here. Thanks for your attention.
Okay, thank you. Questions?
So, what is not clear, completely clear for me, is what observed time means.
What, sorry?
We observe time, we observe interval time means.
Ah, okay, so you mean the spectral lag detected in the observer rest frame, or in the, say, rest, sorry, in the observer frame of reference, or in the rest frame? Okay. So it is a rather tricky point in the sense that there is a lot of literature about the correlation between the rest frame energy and the observer frame range. Because, okay, we can think in a very simple way that there could be 2 sources of difference due to the redshift, in a sense. One due to the time delay, okay, induced by relativity, and one due to the energy, the redshift dependence of the energy, namely the K correction. But there is a study about what collaborators 2012 that show that the correlation between rest frame, spectral lag and observer frame spectral lag is not, they do exist anyway, but it's not very tight. So in order to study spectral lags and not Lorentz invariance violation, it's better to choose 2 energy bands in which we have to transform our observation, the observation by means of only the time delay, and also the K correction, but in an easier way. Also because we have to think that some correction must be anyway integrated, and so this can induce a greater source of bias in the data and correlation. I don't know if I have completely answered to your question, but if you want, I can suggest you some more readings, but I didn't have time to go further in detail.
Someone else? Okay, thank you. So, our second speaker. Allora, Edoardo Iani, black hole regulated star formation in massive galaxies.
Thank you. So good afternoon to everyone. For today's Journal Club, I'll present you a very recent paper that has been published in Nature at the beginning of this month by Martin Navarro and Brody, and the title of which is Black Hole Regulated Star Formation in Massive Galaxies. So the author's aim is to probe the relation between the star formation histories of massive galaxies and the mass of their central supermassive black hole. As a matter of fact, cosmologically motivated theories of galaxy formation need feedback from the supermassive black hole to regulate star formation. In the absence of this feedback, state-of-the-art simulations are not able to recover the observed quantities we see in the local universe, and in particular, I mean the number density and the physical properties of the massive galaxies. I just want to point out that the AGN feedback is something that is expected from theory and simulation, but up to date, up to this paper, according to the claim the authors said, there are no observational evidence of this strongly coupled coevolution between the supermassive black hole and the star formation rate. So, what did they do to fulfill their aim? So they first defined a sample of study, and they started from a sample of very massive galaxies, and they started with the 1022 sources in the HAT Massive Galaxy Survey, a 2015 project led by Van den Bosch at the McDonald Observatory. And they, after having rejected all galaxies with low signal-to-noise ratio, without direct black hole measurements of the mass, and with the strong nebular emission lines, they ended up with 74 galaxies. For each one of these 74 galaxies, they had long-slit optical spectra in the wavelength range in between 46 and 5500 angstroms, and which had a high signal-to-noise ratio, and with a spectral resolution that varies from 4.8 to 7.5 angstrom according to the slit width. They set this to half the effective radius. The effective radius was taken from literature, in particular from measures that have been obtained by Van den Bosch on the infrared K-band photometry. And they choose this particular value for the slit width because, according to them, it's let's say a quantity large enough to allow them in the future to compare their results with simulations, and at the same time, it's small enough to be to ensure that they are looking at in situ star formation. Okay, so let's move on with the spectral fitting. So they adopted a two-step procedure in the spectral fitting to minimize the effect of the spectral of the velocity dispersion and metallicity degeneracy, and in particular they retrieved with PPXF echoed by Capellari the kinematics. So mainly the parameters from velocity and dispersion velocity. And then they run StackMap. StackMap is a Bayesian method-based code which decomposes the spectrum of a galaxy in a temporal series of single stellar populations. And from StackMap they were able to retrieve star formation history. So the first result is this M-sigma relation. So they plotted the mass of the supermassive black hole they retrieved from literature, in particular from this HAT GMS survey, against their measure of the velocity dispersion. These are for the 74 galaxies they found, And this is the main trend of the M-sigma relation. Here, the bottom left corner, the equation. And according to this diagram, they define 3 different groups of galaxies. So the overmassive, standard, and undermassive black hole galaxies. So at a fixed value of the velocity dispersion, if the mass of the black hole is larger than plus or minus 0.2 deaths from the best fit equation, they define the galaxy as overmassive black hole galaxies or undermassive black hole galaxies. For values in between, within this range, we have standard black hole galaxies. So I just want to show you that they obtain for each of these groups a fairly equal amount of galaxies, 25 in both the overmassive and undermassive group, and 24 for standard. Also, the mean velocity dispersion is rather equal. So they're not so different, dynamically speaking. So here, the results on the star formation history. So in the plot on the left-hand side, you can see the star formation history, namely the star formation rate against look-back time, and the small, again, the M-sigma relation, while on the right-hand side, another plot with the cumulative mass fraction against look-back time. Okay, so here in both plots, we have in red the distribution of overmassive black holes, galaxies, in the yellow the average, and in blue the undermassive black holes galaxies, while the dashed areas are for the 1 sigma uncertainties in the mean value, because here we have a sort of mean value for each population, for each group of galaxies. As a matter of fact, before obtaining these results, they normalized the star formation history of each galaxy in such a way that each galaxy from the beginning has formed until now, up to date, 1 unit mass. So what strikes the eyes is that in the star formation history plot, for look-back time greater than 10 gigayears, the star formation rate is higher, is more intense for overmassive black hole galaxies if compared with the undermassive black hole galaxies. And this is also possible to see that it's naturally explained for the authors by the AGN feedback in these sources. And in particular, it's also seen in the other plot, the cumulative mass fraction against look-back time, from the time delay between the moment in which the overmassive black hole galaxies reached 95% of their mass, if compared to the same situation when reached by the undermassive black hole galaxies. So this time delay, this is roughly 4 gigayears, is the reason why it's explained by the quenching due to AGN feedback, mainly. The situation is completely different if you look at younger stellar populations, so for values of the look-back time lower than 10 gigayears. And here we have an upside-down trend. So we have more intense star formation by undermassive black holes, galaxies, than overmassive black hole galaxies. And this is always explained by the AGN feedback, because we have, let's say, a smaller black hole that accretes with a lower rate its mass, and for this reason it's not strong enough, it doesn't release enough energy to maintain the hot corona gaseous hot corona hot. So in the end, ultimately, the hot corona gas cools down and starts forming stars. So here, to the conclusion, so the results suggest that black hole mass growth scales with the gas cooling rate in the early universe, the star formation rate quenching takes place earlier and more efficiently in the galaxies hosting more massive central black holes, and the observed relation between black hole mass and star formation efficiency applies to all generations of stars formed throughout the galaxy life, revealing a continuous interplay between black hole activity and baryon cooling. That's all. Thanks for your attention.
Okay. Questions? Okay, thank you. So, see you next Monday. Bye-bye.